This first video introduces us to a new type of distribution, specifically what's called the chi-squared, C-H-I, chi-squared distribution. And the chi-squared distribution is looking at qualitative variables, so a little bit of a difference from our quantitative cases. This is all dealing with qualitative variables, and it's analyzing a difference between an observed value and an expected value. So when you walk into a situation, you might have some level of expectation that the population might turn. And depending upon those results, we want to see how much did you veer and is it within any sort of reasonability. So did you veer far beyond what you would expect? And what does that imply? Or did you stay within the realm of, expected value? And then it requires the chi-square. So we're going to first introduce a problem to set this whole situation up. We'll talk a little bit about the chi-square, and then we'll answer the actual problem at hand. So let's say that you have a restaurant, and before you start to do some renovations on the restaurant, you complete a survey. So you ask the people, what do you think of the restaurant's food before the renovations? And you say that 15% of them think that the food is excellent, 30% think that the food is good, 45% think that the food is fair, and then 10% think that the food is poor. So you go through the renovations, and then you ask another survey. You ask a total of, if you count all these up, let's say 250 people. And of those 250 people, 46 think that the food's excellent now, 83 think that it's good, 105 think that it's fair, and 16 think that it's poor. So the question becomes, did the renovation do anything? Did it change the restaurant's food for the better or for the worse based on what you originally started with? So what you would expect is similar to the survey originally, and then what you observe, is there a difference between those two? And before we jump into that, I want to just introduce some of the details of this new distribution, our new test statistic that we're going to use for these. It's called the chi-square, like I had said. It's based off of degrees of freedom, so again, the distribution is going to change depending upon, in this case here, the number of categories. The K represents the number of categories. Number of categories. And it's looking at a summation, it's looking at a sum of the difference of the observed value minus the expected value. So what you observe from the actual survey, and then what you would expect based on the previous results. So if there was a drastic change in here, the observed and expected would have a very big difference. We square it to keep everything positive, and then we divide by the expected value. This should look very, very similar to a lot of the other formulas we've been doing, because they're all looking at essentially how far away are your data points breaking from some semblance of central tendency. In this case here, that centralized idea is what you would expect. So is your observed value drastically different from what you would expect, implying that there's a massive change? And again, depending upon the number of degrees of freedom, the distribution is going to change. In this case here, if there were 4 different categories, so there were 4 different possible options that the people could choose from, so the degrees of freedom in this example that we're talking about would be 3. These are going to depend upon also an alpha value. So this is the example of the chi-square table that's in the back of the book. It's going to depend upon a particular alpha value or some percent or some level of either confidence, or if we're talking about a hypothesis test, some alpha value, some test statistic. So let's say for this entire test, let's do an alpha value of 0.05. I'll do that in 0.05. And for an alpha value with 3 degrees of freedom, that would be our critical value. All of these are going to be right-tailed. They're all going to be positive values. So the critical value is going to imply a rejection region, in this case beyond this 7.815. So any value beyond 7.815 is going to fall into the rejection region. Same ideas as the other distributions that we've been dealing with, whether we can accept or reject a null hypothesis. So the first thing you're probably then wondering is, well, what would the null hypothesis in this case look like? And luckily for these goodness of fit tests, if we want to see if there's any sort of change, the null hypothesis is always going to be the same. It's going to be the 4 different, or however many different categories we had, the probability of each of them remaining true. So in this case here, the past survey had, let's say, 15% excellent. So let's say that the hypothesis, the null is that that stays the same. For the good case, the 30% stays the same. For the fair case, that 45% stays the same. And for that poor case, that 10% stays the same. Now, your your alternative hypothesis is going to be that there is some kind of change in those probabilities. It doesn't necessarily dictate what type of change, whether a specific one increases or decreases, but it's just wondering that before and after some sort of circumstance or something that you're comparing the observed and expecteds to, there is some change in the resulting probabilities. Again, nothing in the direction sense, just is there a change in some of these probabilities? Even some of them may stay the same, but as long as one of them changes, there's some change in these probabilities. Okay, so how do we figure out this test statistic? Well, we have to look at all of the observed values, and luckily those are given to us. That's what the original survey says. But the question becomes, what are the expected values? Well, if we had 250 people, if the null hypothesis was true, 15% of them would say that the food is excellent. That's what we would expect to happen. Similarly, 30% would say that the food is good. So to determine the expected totals or the expected percentages, we're just going to multiply the total number of people times the percentage. So if excellent, there were 250 people, and we expected there to be 15% of them to think that the food was excellent, well, then that's going to imply that about 37 and a half people, I know you can't have a half a person, but you would expect 37 and a half people to say that the food is excellent if the percentage is still held. So for 250 times the good, which was 30%, that would equal 75. You would expect 75 people to say that the food was good. Of the 250 people, you would expect 45% of them, or 112.5 people, to say that the food was fair. And then similarly, 250 times 0.10 equals 25 people. And you'll notice that if you add all of these up, it would equal 250. So that intuitively, that should make sense. You're looking at 100% of all possible answers. It should equal your total number of people in the survey. So to find the actual statistic, all we need to do now is just do a little bit of calculation where we take the observed value, so the ones that we got from the survey, minus these values that we expect to happen, and see how far away they are from each other. So for instance, for the excellent case, the survey originally claimed that 46 people thought the food was excellent, but we expect 37.5 people. So for observed minus expected, again, the observed value is 46, minus the expected value, in this case that's 37.5. We're going to take that value and square it, and then we're going to divide that by the expected value, which is 37.5. Couple of things to note again, in the numerator, we are taking the difference to see how far apart those things were. We're squaring them to keep the answers positive and to provide a little more weight to things that are further away from what we expect. And then we're dividing by the expected value to almost create like a z-score type effect. We're really seeing how many sort of, not standard deviations, but how far away a certain value is. And this number is going to be, the bigger the number is, the further away the data point ends up really being. So if you do all this calculation, you do 46 minus 37.5, we square that and then divide it by 37.5, we're going to get a value of 1.93. And if you repeat that process for the other ones, so if we do 83, which is what we actually got from the original survey, so 83, minus the expected value, so we would expect 75 people to say the food was good. We square that and then we divide that by 75. We would get an answer of 0.85. And if you continue with the other two, we would get a value of 0.50, and we would get a value of 3.24. Now the chi-square, the test statistic, is equal to the sum of all of these values. So if we want to figure out the test statistic, we're just going to add up 1.93 plus 0.85 plus 0.50 plus the 3.2 plus 3.24, and that's going to get us a chi-square statistic of 6.52. Now recall that if we were looking at an alpha value of 5%, and let's say that's our significance level, that the critical value was 7.815. So anything beyond that led us to reject the null hypothesis. Well, we're getting a test statistic of 6.52, and since that test statistic is not bigger, it does not fall in the rejection region, we cannot reject the null hypothesis. We cannot say that there have been any changes in the original percentages from the original survey. We can't say that there's been a significant change. If you want to confirm this another way, instead of using a critical value, you can also find a p-value, but it requires Excel. And to do that, we need to use this formula here. It's going to equal CHISQ, so chi-square, dot DIST for a distribution, dot RT, it's always going to be a right-tailed distribution. That's just the way that the table unfolds, so always have RT. And then you're going to use your test statistic that you find and the number of degrees of freedom that are at hand. So in this case here, if you wanted to find the p-value, you type all that in, use your test statistic that we found, so 6.52 with 3 degrees of freedom, and we get a p-value of 0.889, which is clearly bigger than 0.05. And remember that in order to reject the null, we need our p-value to be less than the significance value, not less than the alpha value. So because it's bigger, again, we cannot reject the null hypothesis. So we can see that, again, introducing this chi-square distribution, which looks at comparing what you would observe in a particular qualitative variable minus what you would expect, and then using that to determine if there's been a significant change between a observed value or an observed percent of a proportion and an expected percentage of a proportion.